In this video we will learn about topological sort of a graph. We will learn what is a topological sort, when a topological sort exists and when not, and how to find it. Let's first see what is a topological sort. To make it easy to understand, we will use an example graph that describes the morning routine of Mr. Doug. Each vertex represents a task that Mr. Doug does every morning in his routine. So each morning he brushes his teeth, gets dressed, practices yoga, reads from a book, meditates and eats breakfast. But the order he completes these tasks is changing, so he won't get bored. However, no matter what change he does in the order of these tasks, he always keeps some ground rules. One is that he always gets dressed before practicing yoga. We represent this rule with an edge between these vertices. Mr. Doug also always practices yoga before eating his breakfast. He also always gets dressed before doing a meditation, and meditates always before reading. He also always brushes teeth before reading. Notice that some tasks have to happen before other tasks, and some tasks has no direct ordering between them. Now let's see a topological sort for this graph, but before let's define what topological sort is. Topological sort is a linear ordering of the vertices such that for every edge uv in the graph, u appears before v in the ordering. Here is a linear ordering of the vertices from left to right, which is a topological sort. Let's examine all edges in the graph and see that they meet the criteria of a topological sort. First, for the edge from get dressed to yoga, we see that get dressed appears before yoga in the ordering, so it meets the criteria. Second, for the edge from get dressed to meditations, we also see get dressed appears first in the order. In general, the ordering is a topological sort if all edges go from left to right. The edge from brush teeth to read is going from left to right, so it meets the criteria. And so are the edges from meditation to read and from yoga to breakfast. Therefore, it is a topological sort. The topological sort here ensures the ordering of the tasks meet the rules of Mr. Doug. It is important to note that there are more topological sorts for this graph, and each one is a possible ordering of the tasks in Mr. Doug's morning routine. A simple example for another topological sort here is to use exactly the same ordering, but just swap brush teeth with get dressed. All edges will still go from left to right, so it is also a topological sort. One question you may ask is it always possible to find the topological sort for a graph? Here we have the same example from before. Maybe you've noticed something special with Mr. Doug's name. Doug is actually a shortcut for directed acyclic graph, where acyclic means it is a graph with no cycles. For such graphs, we can always find the topological sort. What if the input graph is not a Doug, meaning it has a cycle? Say we would add an edge between read and get dressed. Now this graph has a cycle, composed of get dressed, meditation and read. Who from this cycle can go first in a topological sort? Option 1 is get dressed. We write 3 dots as we don't mind about the start of the topological sort. Then we have get dressed, and somewhere later we will have read, because we assume get dressed is the first from the cycle. But there is an edge from read to get dressed, so it goes from right to left, which does not meet the criteria of a topological sort. We could also try to put meditation first, but then somewhere later we have get dressed, which has an edge to meditation. So again we have an edge from right to left, so this option is ruled out as well. And similarly, it wouldn't work if we would try to put read first. So the answer for whether a topological sort exists when there is a cycle is no, as we would encounter the same problem we showed in the example here for any graph with a cycle. Okay, let's move on to see how we can find the topological sort. One common algorithm for this is the Kahn algorithm. We start with the idea of Kahn algorithm and later we will see the pseudocode and the full example. But before, let's define what in degree of a vertex means. In degree of a vertex is simply the number of incoming edges it has. Specifically, if a vertex has in degree 0, it means it has no incoming edges. The idea behind Kahn algorithm is to gradually build a topological sort by adding a vertex on each step which has in degree 0 or no incoming edges, and remove it from the graph. In the example here, we can start with either brush teased or get dressed, since both have no incoming edges. We choose get dressed and add it to the topological sort. We then remove the vertex from the graph together with its edges. Now we repeat and continue with brush tease, which has no incoming edges. So we add it and remove it from the graph. Now we can add either yoga or meditations, since both has no more incoming edges. We choose meditation. Notice that meditation originally had an incoming edge, but we already removed it when adding the vertex connected to it to the topological sort. We then similarly add read and remove it. Then we add yoga and remove it. And lastly, breakfast. Here is our graph again. Notice it is a valid topological sort since all edges go from left to right. Now that we are familiar with the idea of Kahn algorithm, let's see the pseudocode of the algorithm. The input is a directed graph G, which is represented as adjacency lists. If you'd like to learn more about adjacency list representations, please follow the link from the description below. But don't worry if not, you likely understand the algorithm anyway. The algorithm starts by calculating the in degree for each vertex. We do that by first looping over the vertices and initialize the in degree to 0. Then we loop over the vertices again, and for each neighbor in the adjacency list, we increment the in degree. Since we found an edge that is connected to it, we then init an empty list L, which will hold the topological sort, and an empty queue. We then add all vertices with in degree 0 to the queue, to be processed first. We do this by looping over the vertices and checking the in degree we calculated before. Now, while the queue is not empty, we add a vertex to the topological sort and remove it from the graph. The quotes are because we don't really remove it. We do this by first dequeue a vertex from the queue. We then add it to the topological sort. Remember, at start we only added vertices with in degree 0, so we know this vertex can be added to the topological sort, as there will be no edge from any vertex connected to it. And the remove part takes place here, by looping over the neighbors in the adjacency list, and for each one decrease its in degree by 1, meaning the edge from the current vertex we remove no longer impact the in degree. If by doing so the in degree of the neighbor is 0, we add it to the queue. Adding it to the queue means it can be added to the topological sort, because we already added all vertices that have an edge into it to the sort. When the queue is empty and we exit the while loop, there are two options. One is that we handled all vertices. In this case, the size of the topological sort is as the number of vertices v. If this is the case, we return L as the topological sort. The other option is that we don't have all vertices in the sort. This can happen if the input graph G is not a DAG. Remember before that we talked about that a directed graph should have no cycles in order to have a topological sort. So this algorithm works on any directed graph, but it only returns a topological sort if such exists, otherwise it returns null. It means that the algorithm can also be used to check if a graph has a cycle or not, which is nice. Let's run the algorithm on our example graph. Here we have again the same graph we've used before, and on the left we have the pseudocode. We start with calculating the in degree. We don't go over it step by step and just write next to each vertex its in degree. For brush teeth it is 0, since it has no incoming edges. Read has 2 incoming edges, so we write 2. Similarly, we write 0 for get dressed, 1 for meditation, 1 for yoga, and 1 for breakfast. We then init the empty list L and an empty Q. Now we loop over all vertices and add vertices with in degree 0 to the Q. We see that brush teeth and get dressed have 0 in degree, so we add them to the Q. We then continue to the while loop and enter since the Q is not empty. With the Q get dressed as it is the first in the Q and add it to the topological sort. We then loop over the neighbors of get dressed, which are yoga and meditation, decrease their in degree by 1, and since their in degree becomes 0, we add them to the Q. We finish handling get dressed, and we go back to the while loop and start another iteration since the Q is not empty. We now the Q brush teeth and add it to the topological sort. Brush teeth has only one neighbor, which is read. We reduce read in degree by 1. Its in degree is not 0, so it is not yet ready to be added to the Q. So we go back to another iteration of the while loop. We now the Q yoga and add it to the topological sort. Yoga has only one neighbor, which is breakfast, so we decrease its in degree. And since it becomes 0, we also add breakfast to the Q. We continue to another iteration of the while loop. And we now the Q meditation and add it to the topological sort. Meditation has only one neighbor, which is read. We reduce read in degree, and now it becomes 0, so we add it to the Q. We move to another iteration of the while loop, and now we handle breakfast. We dequeue it and add it to the topological sort. Breakfast has no neighbors, so we move to another iteration of the while loop. We now dequeue read and add it to the topological sort. We see read has no outgoing edges, so we go back to the while loop. And the Q is now empty, so we exit the loop and move to the if condition below. We see the length of L, the topological sort, is 6, which is the same as the number of vertices, which means the topological sort is valid, so we return it. We ended with a different topological sort from before, but it is still a valid one, because all edges go from left to right. Remember we said that if there is no topological sort, we will return null, as the last line in the pseudocode. To make it a bit easier to see, let's assume for a moment that there was another edge here between read to get dressed. Running the algorithm on this graph, we would start by calculating the in degree, and see that get dressed now has in degree of 1 instead of 0 as before. So brush teeth is the only vertex added to the Q. Then we will dequeue it and add it to the list L. Then, when looping over its neighbors, we will decrease by 1 the in degree of read, which is not enough to add it to the Q. So we would return to the while loop condition and exit the loop, since the Q is empty. The list length is 1, and not as the number of vertices, so we return null. Let's now talk about the time and space complexity of the algorithm. Here on the left we have the pseudocode of the algorithm. We start with time complexity. First, we have two for loops for calculating the in degree. The first for loop is doing operation of constant times for each vertex, which the time complexity of is big O of the number of vertices v. The second loop goes over all vertices as well, but for each one it goes over all of its outgoing edges. For each edge doing operation of constant time. In total it goes over all vertices and all edges once, so the time complexity of this is big O of v plus e. And in total, the part of calculating the in degree is therefore big O of v plus e. Then we have initialization of the list and queue, which is of constant time, so it is big O of 1. Next we have another loop over the vertices in order to enqueue vertices with in degree 0, which its time complexity is big O of v. Then we have the while loop. In each iteration of the while loop we have operation of constant time, such as the dequeue, and the loop over the outgoing edges. So each iteration costs big O of 1 plus big O of the number of outgoing edges. How many iterations do we have? Key understanding here is that each vertex is enqueued at most once, because a vertex is added to the queue only when its in degree becomes 0, which happens at most once. Therefore, the cost of the while loop, by aggregating the iterations as the number of vertices, is big O of v plus e. Finally, we have the return decision, which costs big O of 1. So in total, by summing it all up, we are left with big O of the number of vertices v plus the number of edges e. What about the space complexity? Well, we have the list L that saves the topological sort, which can grow to the number of vertices, so it costs big O of v, and the queue, which at the worst case can grow to the number of vertices as well, so it costs big O of v as well. Therefore, in total, our space complexity is big O of v. Thank you for watching. If you like this video, please don't forget to hit the like button and subscribe to the channel.